Okay, good evening, everybody. Welcome to our March Mixer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it's understood that you've accepted these terms. Okay, so on tonight's agenda, we have Charlie V3 KCC on how coax provides a path of bringing RF into the shack and the things you can do to stop it. After that, after any questions and whatnot, we'll move on to the roundtable. And if anybody else has anything else to talk about or ask questions of other nature, then of course they're always welcomed. So I guess, Charlie, if you're ready.
Yeah, I think so. Just one quick correction, Peter. It's VE3XCC, not KCC.
Oh, Casey. You know what? I looked at that and I thought that doesn't sound right because it sounds too familiar of Casey. All right, sorry about that, Charlie.
Hey, no problem at all.
Okay.
Let's see if I can figure out how to share the screen here. Start screen sharing. That looks good. Oh my goodness. So many options. Giving me a bit of a challenge this evening finding the screen I want to. Oh, I see. Okay. Screen. I'm not sure why Jitsi wants to give me troubles, but all right. How's that? Can you see this title page?
Yeah, we can.
Okay, great. So this is probably a good chunk of the discussion this evening is pretty 101-ish, maybe a little bit simplistic for most of the folks on the call, but we'll see how things go. In the beginning, I wanted to talk about RF in the shack. This is another one of the many rabbit holes that we can end up going down. And after much digging into an RF in the shack problem I was having a while back, I found an interesting article by Steve Hunt in the UK, who really was talking about common mode chokes. And so there's a lot of material here I stole from him. There's also some additional material from some corporate presentations that I think might be worthwhile looking at. So when it comes to RF in the shack, it's nasty stuff, right? It reboots your computer, plays havoc with your other systems. You're trying to make measurements and they turn out incorrect for some reason. And if you've really messed up and the RF is really bad, you can actually burn your fingers on it. So where's it coming from? How does it get in? And how can we prevent that from happening? There's a couple of kind of basic concepts we need to get comfortable with before we can tackle those questions. They are, first of all, the concept of skin effect. So I don't know how familiar you are with this, but RF behaves quite differently compared to DC. Skin effect is one of the cool things that happens with RF. The currents actually only flow in the outside edge of a conductor. And recent research says it actually only flows down a few atoms deep into the conductor. So it's really just on the skin of that conductor. It can also get kind of pushed more to one side or the other of a conductor with magnetic or electrical fields. So while it, if there's nothing going on, it'll be fairly equivalent down all around the edges of a round conductor. But if there's an electrical field, it might get pushed to one side. So, what this implies is that a hollow conductor behaves exactly the same as a solid conductor. So you can save an awful lot of money by using a pipe instead of a wire. For example, a length of 1/8 diameter copper tubing which is easy to find in pretty much any hardware store because it's used for refrigerant stuff. It's going to behave the same as a number 8 solid copper wire, but of course at significantly lower cost. So skin effect can help us out when it when it comes to cost reduction and so on. But of course, it impacts more than just the cost, and if you're not careful, it can actually work against you. The second concept that's important to understand how the RF gets back in the shack is transmission lines. The standard 2-wire transmission line that we've all seen and used over the years looks something like this. It's got a kind of a standard generator, and it's got a load impedance, and current goes out one of those 2 conductors and comes back in the other. That's differential mode currents flowing. And kind of basic Ohm's law stuff, if current is going out one conductor, it has to come back in the other. There's no free lunch, nothing goes anywhere else. Everything is completely contained in that transmission line. Having said that, if you look a little more closely at it and you start thinking about the skin effect thing, with open wire transmission line, those opposite charges attract, and the electron density is mostly on the side between the conductors, actually. External forces can change that charge distribution. If there's a magnetic field or a chunk of metal or something, it might push the flow to the other side of the conductor in that particular area. But generally speaking, it tends to be between the two. The charges sort of attract or repel each other and stay on that inside of the conductor pair. And of course, if you've got something that's interfering with that, then potentially you can get into situations where things start to radiate off those 2 wires. So having said that, coax is really cool. We use coax all over the place. And if you put those sort of 2 concepts together that I spoke of earlier, you've got your center copper conductor. You've got a thin layer, only a few atoms thick on the outside of it, that is the current flowing out. This is kind of an in view of the coax. Then you've got the material in the center of the coax that's an insulator, and then you've got the outer shield of the coax, and the return current, the current that's going out in the center conductor, tends to come back on the inside of the coax because these 2 fields are somewhat tangled together and interested in each other. So this outer conductor acts as a very nice shield for things. All the currents that we're interested in for our circuit are contained inside the actual coax, with the outgoing current flowing along the edges of the center conductor and the return flowing along the inner edge of that outer conductor of the coax. So a third concept that's important here is the concept of common mode currents. And really, these typically happen because of an unintended current paths. If you've got current from this generator going out, let's say the center conductor of a coax, goes through the load, a portion of it comes back on the inside of the outer shield, but another path can occur which has the current flowing to ground somehow through a load impedance of some flavor. And of course, since that ground ends up with this ground over here, you've now got current flowing out here that does not come back in this path, but rather uses this IC path to come back. That is the common mode current. So current that is, you can create a technical argument where you've got current flowing this way and a certain amount of current flowing this way, so that the two currents here are common. The one that's going this direction subtracts from the current that's going in this direction, and therefore this other return path that's out here is, the two currents here are effectively common with the return going back through this ground system. Whoops, did not mean to do that. So, the math on this is pretty simple, right? What goes out must return in some fashion. So if you've got the IA going out here, then whatever current here I see through this unintended current path plus the IB must be equal to the IA. It's again, whether the current is coming through here or coming up through the ground, everything that goes out must come back in some fashion. Now this is where coax actually hurts us. Because of the skin effect, coax actually effectively has three conductors, not the two that we typically think about. So you've got, the center conductor with the current flowing along the skin of it on its way out. You've got the shield with that current IB basically coming back in on the inside of the shield. But there's a completely independent, few atoms thick conductor on the outside of the shield, which the common mode currents can flow along. And so even though, coax we think has two conductors, in fact, in truth, it actually has three. So, how do we get that unintended current that's flowing back on one of that outside conductor? There's a whole bunch of ways this can happen. Basically, any imbalance, things like that. And, as amateurs, we do it to ourselves all the time, right? Like one of our favorite setups is we set up a dipole antenna, and then we bring our coax out to it. We connect the center conductor to one side, and we can connect the shield to the other side. And lo and behold, we think everything works, but wait, there's some RF coming in the shack. And that's because some of that current that, should be headed out this particular leg of the dipole is in fact bouncing back along the coax. Here's a model of the using EasyNet, which lots of us use, that shows just how nasty this can be with an impedance, right? So, rather than taking an unbalanced signal here and converting it to a balanced signal and then doing a bit of a transformer to match the kind of 72 ohms, which is nominally the impedance you'd expect at the center of a dipole, matching to the 50 ohms of the coax we typically use, you can see what all that, bad mismatch actually does for the current flow in the conductors. And you can see that, one leg of your dipole has got a current flow, a nice big maximum current flow at the center, like we'd expect. But the other leg, that B leg, isn't getting the current to radiate that we'd expect. In fact, a very large portion of it ends up bouncing back along the outside edge of that coax. Another example of how we do this kind of thing to ourselves is, we say, okay, we're going to use ladder line. We're not going to have coax in the system, and then we don't have to worry about this, conducted RF coming back in along it. But then, if we're using a doublet or a ladder line system, at the end of the day, we end up using an unbalanced tuner. And that unbalanced tuner, yes, you can kind of tune out the mismatch as far as your radio is concerned, but those currents are still going to come back, along the outside of this chunk of coax here between the unbalanced tuner and the ladder line system. And gee, lo and behold, we've got RF coming into the shack again. So having said all of that, how are we going to fix this? I guess the first thing is the old joke, doctor, it hurts when I do this. And the doctor replies, well, don't do that. So we should do everything that we can to reduce accidental common mode currents. And we can do that by, things like matching impedances, using unbalanced balance converters, those sorts of things. But the reality is that it's pretty much impossible to completely eliminate those common mode currents in the real world. I mean, maybe you can get them small enough that you really don't care, they don't impact what you're trying to do, but trying to get a perfectly balanced feed line system is almost impossible. So try and reduce them. That's a good thing. But if you can't do that, the other method is to try and make it difficult for those common mode currents to flow along the outside edge of your coax by significantly raising the impedance to RF along the outside of the coax. And typically this is done with some flavor of common mode choke or ferrite beads. And it's worth noting, it's one of the cool things about coax is that anything we do to impact those common mode currents, they're not going to impact the differential mode currents of our signal inside the coax. Those are nicely contained on the inside of the coax, and the things we do on the outside don't impact those at all. So that's one of the nice advantages of coax for us. So the first thing when we go and dig into our toolkit of how the heck do we stop this stuff from coming back into the shack is we start out, we make an ugly bellend. I think everybody's made one of these at least once. It's kind of one of my favorite go-tos. And well, because they're incredibly easy, right? All you need to do is basically coil up a handful of coax and you're done. Just to be clear, at the beginning of this, an ugly bellend is not a bellend at all. It does nothing in the way of balance to unbalanced conversion. It's really, it's a common mode choke. One of the things you'll discover when you start playing with these, and if you could actually dig in and measure their capabilities, you'll start to discover that you need way more turns than you think you did, first off. And secondly, the diameter of that coil of coax, if you like, makes a huge difference. If you make a fairly small diameter, it won't be nearly as effective. Something with a 4-inch diameter, for instance, won't be nearly as effective as something with, say, a 12-inch diameter. The other thing is this circuit arrangement, has a reasonably high Q. I mean, it's not, fantastic. I wouldn't use it for a transmitter, but it's not exactly flat across the band of interest for us either. So, the blue line here is the typical standard line for these things. This particular one that was measured was 5 turns of RG58 with 4¼ inches in diameter, tightly wound, coupled together, not made in too big a mess. And you can see that it's got, a very high peak of impedance here, over 10K ohms, 20K ohms actually, at about almost 35 meg. And then if you get down here into the, into the 160 and the 80 meter bands, well, you're looking at 100 ohms, a couple hundred ohms, not a ton of actual impedance being created. The other thing that's interesting to note with this is that a little bit of stray capacitance can really pull around where this peak is. The red line is 2.2 picofarads of stray capacitance, which you can get by putting your hand close to it, right? And it's pulled the frequency down here, darn near 10 meg, right? Maybe more. So it's, well, the ugly bellin will help you a lot for sure. It's very subjective to any kind of stray capacitance that's rolling around. It's kind of peaky. It doesn't give you a flat response, and it's you need an awful lot of turns to start doing good things down here in the 160 meter space. Which begs the question, actually, how much impedance is enough? If we're going to add some additional impedance to that outside coax path, what should it be? And to be honest, this is subjective, and there's lots of opinions around. For me personally, I like to try and make that impedance maybe 10 times what the primary path impedance is. So if we're using 50 ohm coax, I want to try and make about 500 ohms at the lowest frequency of interest. Doing some online research, I did find a number of sources that suggested 4 times would be sufficient. So something in the order of, say, 200 ohms might be good enough. But for your mileage might vary. if you're playing with 10, 50, 100 watts, maybe it's not a big deal. If you start pushing a kilowatt, you may need some higher value impedances there. So if you can get to 500 ohms, that's awesome. That's probably good enough for anything that we as amateurs would want to do. So let's say for this 500 ohms at 160 meters, that works out to 4.42 microhenries. Is what we want our choke or coil to be. And if you find some online calculators that tell you how to figure out the impedance of your ugly ballon, this works out to about 5 turns tightly coupled on a 12-inch diameter. So you need about 15 feet of coax just for that ballon. Anything beyond that's better. And the other thing worth noting is that the inductance has a linear relationship with the permeability of the core. It has a square law relationship with the number of turns, but whatever the permeability of the material that you're winding it on is, that relationship is linear. So the ugly balance core is air, which has a permeability of 1. If we replace that core with, say, an FT24043 toroid, well, that permeability goes up to 850. So the impedance goes up 850 times. So consequently, we can, of course, reduce the size of the coil we're making and the number of turns we're making. And it's just far, far more effective to wind it on a toroid than it is just to make this coil of coax that we throw on the ground with a piece of wood over the top of it. For those folks who actually make toroids, this should be a pretty familiar picture. This is some RG174 going through 3 layers actually. You count the turns by the number of times it passes through the center. So there's, I think, 7 turns on this one. And this is a far, far better common mode choke than that ugly ballon we talked about earlier. In fact, this is what the graph looks like. You can see that it's significantly flatter. It's moved it down in frequency. This is these two plots here, the green line is the real component of the impedance, so it's the effective resistance, whereas the red line is the plus JX of the coil. What you can see here is that, if for our 50 ohm coax, we want to get to 10 times that, so 500 ohms, that's this line here. So you can see that in terms of frequency, we've got 500 ohms at 80 meters for sure. And we still, even at 160 meters, we've got, a reasonable amount of impedance with these, in this particular case, 9 turns on the 3 stacked FT240 52 toroids. Our buddy Steve in the UK, that I stole a lot of this information from, actually spent a bunch of time going through these inductors, common mode chokes, wound on toroids, to basically say, to create this chart of, depending on the frequency of interest and the number of turns you put and the type of material you're using, what exactly can you expect of these common mode chokes? So, the key down in the corner here is if it's red, it's more than 500 ohms, and beyond that, it's even better. So you can see that, 17 turns on the 240-31 is going to be great for our very low frequency stuff, and still extremely good all the way out to the top end of the HF band. In fact, the only ones that start to give us issues is the FT240-52 material, which starts to cause some issues down here in the 160 meter range. So if you stick with the 43 material, you're going to be in great shape, no matter how many turns you choose to put on this thing. Ferrite beads. So this is the other thing that I got burned on a time or two. When it came to VHF, I'd have RF coming back in from a J-pole or something, and I thought, oh, well, I'll just grab one of those clamp-on ferrite beads and throw it on there, and life will be good, and I can move on. And I threw one on, didn't make a whole lot of difference. I threw a second one on. It got better, but still not great. And I had to put, 3 or 4 beads on the outside of the coax. At the time, I wasn't keen on understanding why that should be so. I just wanted to get the darn antenna working. And so I left those beads on there for a long time before I actually started digging into what the beads were really doing. These charts come from TDK, actually, who's the manufacturer of ferrite beads. And so they show the sort of the real and the imaginary component of the impedance that you would expect at various frequencies of, the ferrite beads that they particularly sell. So this MPZ, well, I won't go through the entire number of it, but it's specified to have 1,000 ohms at 100 megahertz, and you'll typically see higher frequency stuff here because beads tend to be used at higher frequencies than the HF stuff. But even when you get down into that, 10 meg range, or 14's in here, so the 20 meter band is in this kind of space, you still got some pretty good numbers here. You're still in the, beyond 500 ohms. You're in the 700-800 ohm region. Then as you start to drop down, get down into the 40 meter area, well, not so great. You're probably looking at 20-30 ohms at most per ferrite bead. So, as the frequency goes up, these things are definitely much higher value for you. For HF stuff, I think you're better off using a toroid and looping a physically smaller coax through it as many times as you can. Ferrite beads actually do some pretty interesting stuff. So, at the lower frequencies, they behave like a low pass filter, where the current basically shunts to ground. When you get to the middle frequency ranges, it still looks like a low pass filter, but now instead of looking like an inductor in the center element, it looks more like a resistor, and you get the energy being dissipated as heat now. So you can actually physically feel these things getting warm if the RF that you're trying to get rid of is in that kind of center frequency area. And then once you get on into the upper sections of it, it starts to look like a high pass filter. So it's not really doing much of anything in terms of getting rid of RF for us. It just kind of blasts straight on through. So, beads have their place. They're very good at getting rid of noise, good at things like switching noise, things that are very high frequencies. But for lower frequency stuff, they get kind of wimpy at the low frequency end, they're kind of wimpy at the high frequency end. You really need to understand the frequency of interest that you're trying to get rid of with a lossy substance if you are planning on using ferrite beads. The other interesting thing about ferrite beads is the impact that DC has on them. This one I found really quite shocking. So, here at pick your frequency at 10 megahertz, let's say. At 10 megahertz, we're looking at about 300 ohms with no DC on it at all. Suddenly, you introduce just 0.3 amps, 300 milliamps, and the reactance goes way down here into the kind of 15 to 20 ohms region with just a very small amount of DC current. So short answer is don't put these things on your DC power leads. Don't put them on the 12 volt supply for your radio, because they'll stop being useful very quickly. And then as you increase the current, they get even worse. These other numbers are each one of these lines is an additional 300 milliamps. But this first step is just massive, like it's an order of magnitude worse with a very small amount of DC current. And I think that is pretty much what I had to say this evening. Are there any questions? I'll just drop out of this so I can see the screen again.
Okay, thanks for that, Charlie. Yeah, a couple of things there I did not realize, especially with the skin effect. Well, I'm aware of skin effect, but I didn't realize that the electrons were running on one side of the conductor. I thought it was evenly distributed around. But in talking about skin effect, is it frequency dependent, or it just doesn't matter? 1 hertz all the way up to whatever, all on the outside, all on the outside of the conductor.
Good question, Peter. At DC, it's pretty much constant through the entire conductor, and it gets less and less deep as the frequency goes up. I don't have any data to say where it moves to that 3 or 4 atoms thick on the outside edge of the conductor, but it is relatively low frequency when that starts to happen.
Does power come into the equation at all, or is it just the frequency is what makes it rise to the surface?
It's the frequency.
Okay, thanks. Kevin.
Hi. Yeah. No. I was just going to say as far as I know, the skin depth it's inversely proportional to the frequency, so the depth goes down as 1/f. So
Makes
to
sense.
Charlie's point, it's frequency, and even to the point about tubes, it's like at Bruce, like the power conductors coming out of the main generator are like 2 foot diameter copper tubes. They're not solid wires or bus bars for that reason.
I never thought about it. When I was an apprentice, I was doing a substation, and it was all the conductors were not solid conductors; they're all tubes. But of course, I didn't have this meeting back then, all those years ago, where that's journeyman why. But anyway, Drew, you're up next.
Yeah, it was really good, Charlie. Size of coax. I fairly limited 50 ohm coax going through a 240. You're pushing it to get 6 or 7 through there. I have some 174 and I've used it in a smaller toroid. I'm assuming the power handling capabilities of the coax greatly influence how well you can do this.
Yeah, it's the physical side of the conductor, right? Like
Yeah.
it's surprising how much current 174 will actually handle, how much RF current. I was surprised. What really starts to become an issue as you get into the higher powers is the voltage breakdown, right? So that's where the physical distances come into play.
So with 100 watts and I use a 140 toroid, is it more of a heat issue that's a limiting factor?
Um,
Is there a lot of heat attached to a common mode choke?
I guess it depends. How badly mismatched is the load that you're trying to get towards? So how much of the current is flowing in the outside conductor?
Yeah.
And what you're really doing with the common mode choke is you're pushing up the impedance. So it's a V squared over R, right? So as the impedance goes up, the amount of voltage and current, the amount of current flowing on the outside of that goes down consistently. So you basically have to, it's Ohm's law. You just got to sit there and do the math and decide how many watts you can put in. And maybe you need a second toroid on top of the first one to give it a bit more power handling capability.
Well, it helps a lot when you said that it's the voltage breakdown you worry about with the size of the coax more than anything, because that helps a great deal. Because I like the 174 and it's very convenient for, I think, up to 100 watts. I think it's okay.
Mm-hmm. Yeah, I agree.
Yeah. Good, thanks.
It's just something's just occurred to me, Charlie. Let's see if I word this right. We take a particular wire size, and we know the current carrying capacity of this wire size. But if we now all of a sudden have to take into account, due to the skin effect, said current won't be used in that whole conductor. It'll just be using a small portion of that conductor. So that seems to me you need to think about derating. So what you think of a cable that's, say, can take 10 amps of power. In fact, if you need 10 amps of power, just to pick a number, you'd have to increase the size of your conductor because it's all going to be running on the skin effect. So what's the derating factor?
Yeah, I can't answer that, Peter. I haven't dug into it, but you're absolutely right. That is something you need to consider for sure.
Anybody else have any other questions or comments? Dave.
Yeah, hey Charlie, I missed what you said about ferrite beads. Now, when you're talking about ferrite beads, are you talking about the clamp-on type of chokes you can get?
Yes, Dave. That's what So I found a good deal on them from China, and I bought a bunch of them, thinking I was going to solve world hunger with them. Turns out they weren't nearly as effective as I thought they were, and then I kind of dug into why that would be so. TDK makes a very good quality product, and so the charts that I used I actually got from their website, where they talk about those beads.
Yeah, because I got mine from DX Engineering. I
Mhm.
I put them on. They don't work well, but let me just show you something here, because this was a where's share my screen. So this guy's video here, where he talks about he has this rig and he connects it up, and he puts a number of them on and he measures it, and he was saying like between 5 to 7 is sufficient. Now, however, if you look at the curve at high frequencies, it's good, but to your point, the low frequency side's not good, and that's where I'm getting a lot of my um, uh, feedback into my shack is from the low frequencies.
Yeah, you'd do much better with grab a toroid and loop your coax through there as many times as you can. And, something like a 43 ferrite mix would be ideal, I think.
Yeah, or you get because I was looking at DX Engineering and just getting a choke that's molded. It's got two PL 259s, and you just screw it on, right?
Yep. Yep. No, that's certainly a good way to go. Um, the it's interesting to see that picture of how he was actually attempting to measure these things because that two puff capacitance pulling the frequency that I showed early on, that was using a VNA in an S21 configuration, so out one port, back in the other, and then where the output signal was coming out into the circuit of test, a two puff cap to ground at that location pulled that frequency like 10 megahertz. Like, it was incredible the amount of impact it had on that ugly balun. So um, yeah, it's that. I mean, if you're doing VHF or UHF stuff, ferrite beads are a good way to go. They're cheap, easy. You can clamp them on and snap them in place, and life's good. I use them quite a bit actually on things like like APRS units and whatnot, between the computer and the radio, just to keep RF from wandering back in and messing up my computer. But when you get down into the HF stuff, the beads are they're not going to do it for you. Look for a toroid.
Drew.
It's interesting that you mentioned about the beads and HF. The typical fashion for creating a G5 RV
Mhm.
was to have 28 feet of 300 ohm go into a dipole, and you would stack that 28 feet with beads, a bunch of them. And there was always a huge debate about whether you needed the beads or how many beads. And some people would simply fill up 28 feet with as many beads as they get their hands on.
Wow.
And from what you're showing me, it really doesn't matter. It's never really going to do any good at the lower frequencies.
Well, given a bit of distance between the beads, some portion of a wavelength, I guess. Um, if your bead it adds 20 ohms, give it a little bit of a space, then put another one. You got another 20 ohms, a bit of space, another 20 ohms. So yeah, it will help eventually, but you want to get to 500 ohms. That's an awful lot of beads.
Well, that's what I was getting at. Is that there was a lot of beads, but they never put a space in between them. They stacked them and then they put heat sink over or heat shrink over them.
The
So
other
it was a
thing
funny
with
looking rig.
the other thing with that style of antenna is, um, that the transmission line is really behaving as part of the antenna. It's like an end-fed half wave. You need a few feet of coax before you actually get into chokes and whatnot, and that behaves as a counterpoise, which makes the antenna much more efficient. Gives it something to push against, which is another big area of debate. I think is, do you need a counterpoise or not, and what the heck is it, and what's it really doing? And let's not get into that tonight because we don't have that many hours.
Well, just before I don't want to dominate here. On the UHF VHF side, you were using a clamp on ferrite.
Yes.
Okay, so it's just the plastic like you would put on a monitor.
Yeah, yeah. I like I say,
Okay.
I found a bunch of them of different physical sizes. I found some in 3 millimeter, 5 millimeter, 7 millimeter. Depending on whatever cable I'm using, I would put a few of those on. And at UHF, they're great, and even at VHF, they're not bad. But at HF, they're pretty much useless.
Yeah. Well, it's just I have UHF, VHF, and I have noise, so that will help. That I do have those. I'd never tried it. Thank you.
Kevin, you're up next.
Hang on, I'm muted. Okay. No, I was looking up when you were talking about the power rating of the 174 cable, and what a difference between like some of the less quality manufacturers and something like a Belden.
Mm-hmm.
Belden handles over 200 watts at 30 megahertz on R74, 174, and it's rated for 1100 volts. I could not believe it. Even at 150 megahertz, it's still 74 watts.
Yeah, it's
That's
really it's the
it's
dielectric,
amazing.
right?
Yeah, that's amazing. Some of the other ones were rated like 30 volts and like 15 watts
So you're saying
on
my Amazon
174.
174 isn't a good one to rely on?
Well, it depends
Well,
on the dielectric.
do you care about your rig?
Well, that's yes. I'm pretty sure it's
Well,
not Belden.
honestly, Drew, it's it's the old RTFM, right? Dig into the data sheet and see what it really says that it's capable of handling.
And yeah, and as somebody that works in the wire and cable industry and has been in these factories, yeah, there's a big difference between some manufacturers, and I'm just talking the onshore ones. So anyway,
That's very interesting.
Any other questions for Charlie? Okay, great, Charlie. Thanks very much. Very informative. Thank you.
Thanks, guys.
Okay. One thing I'll ask of the group here is if anybody's thinking about, well, actually, even if you're not thinking about it, how about thinking about maybe doing some presentations? You could certainly use some looking to fill up our schedule. Doesn't have to be long, could be any length, couple of minutes to 30 minutes. We always have room for short presentations as well. Another thing I think we started the odd time was show and tell. So, think about maybe what you can do for a show and tell. And maybe best might be a couple of pictures that you can do a share screen of whatever project you're working on or whatever is interesting of you. Might be an idea. If any ideas for a topic of interest that we could discuss, send them my way. And if there's any changes you'd like to see what we're doing and improvements we can make, again, just send it to me and we can go from there. Okay. I guess we can go on to our roundtable. And since I'm at the top left, I'll start. So I did take, I've been working on the Active Probe, of course. What else is new? Although I did take a break this week I discovered a couple of things that made me throw in the towel for a few days. I'll be getting back to it shortly. But basically, I'm going to go back to MOSFET school again and take Dave's advice on a couple of things, and we'll go from there. No rush to finish it, really. I mean, we can make it work, but can we make it work the way we really want to work? That's going to be the challenge. I'm starting to see why Tektronix and the likes are charging thousands and thousands of dollars for these probes. Let's see what else was going on here. Oh, this week I downloaded KiCad 8. And I started to play around with importing LT Spice files into that version of KiCad, and just seeing how KiCad handles those .asc files. So I'll probably do a little short presentation on that at some point. So that was quite interesting. And locally here, there's been a little bit of a revival. I remember some of us were playing around with HackRF and dongles and whatnot. And Phil here, HST, has started doing some slow scan TV stuff with transmitting with the HackRF using GNU radio. So that's got my interest going again. I should dust off HackRF and going, which of course is now going to mean I have to start thinking about an RF amplifier at those frequencies. Oh, great. I can hardly wait. Anyway, so with that, we'll move on to the next. So the next one on my screen is Dave. What's on the bench, Dave?
Oh, Um, I've been working on my beacon for mostly working on stuff for the eclipse because I'm getting ready for the eclipse. It's about a month away. It's the 5th today. It's just over a month away. So I'm working on that, and as well, I'm working on this piece if my camera ever comes up. So this is my solar tracker. So I've been building this. This is going to track the sun. I'm going to have a whole bunch of sensors here to measure, ultraviolet light and infrared and all kinds of stuff. So the idea is this is going to track the sun during the eclipse, and I'll make measurements. It'll have a camera, so I could take pictures of the eclipse with the appropriate filter, of course. So that's kind of what I've been. It's kind of what I've been working on.
Oh, very good, Dave. Thank you. Unfortunately, I'm not going to be here. I'm going to be over in Europe for the eclipse. I was debating whether I should even mention that to the XYL and the family that's all going on this trip, but I thought better. Al, good evening. What's on the bench?
Good evening. Well, not a whole lot, work's in the way, life's in the way, but I'm doing more repair work than anything else. I just finished this weekend repairing one of those Tivoli radios. They have an Achilles heel where the tuning capacitor is one of those polyvaricons, and they wear out. And then when you turn the knob, all you get is static. So was able to find something in China and soldered it in. A little bit of, I'll say open heart surgery, but it actually worked. Actually, I do have a bit of a question for anybody that's running one of those, the spectrum analyzers. I brought it up earlier, and I think the consensus was go buy something from RCC Electronics, model was it, 3021. And I've been on their website looking around and trying to figure out the different options and the price point. And a couple of things I noticed is for an extra $200 or $300, you can get your resolution bandwidth down to 1 hertz rather than 10 hertz. Doesn't sound like a bad thing to go for. The other thing I was wondering is the ultimate frequency range on this. I think probably was it Peter, Dave, and Michael were using the 2.1 gigahertz machine, and they do offer a 1.5 gigahertz machine, and again, it's $200 or $300 cheaper. And I was really kind of wondering to myself, do you pick the high-end frequency response like you would in an oscilloscope, where you want a fair bit of headroom over and above what you're planning on using? I don't think I've ever used anything in the gigahertz. I'm not sure I ever will.
I don't think, no, it's not the same. And you're right. Their bottom end, the spectrum analyzer goes to 2.1 gigahertz, right? So,
they have one at 1.5.
Oh, do they? Well, that must be good.
It's another $300 less. So
how much less?
I think it was about 300. By the time you got the plus, which was the low resolution bandwidth, and the 1.5 gig, you were talking about $400 or maybe almost $500 landed cost difference.
Unless somebody, Dave or somebody, knows differently, I would probably go for the cheaper one, to be honest with you, because I don't use anything up in gigahertz. I barely get into let alone get up to that other stuff. Although one never knows.
Yeah.
As far as the 1 hertz, I don't know. I thought mine went down to 3, maybe 1. I can't remember now.
The models that have the word plus attached to the number go down to 1.
Okay, so mine has the plus on it, so it does go to 1. But boy, it's pretty slow when you go down there. I don't go down there very often, but it does when you need it, you need it. Dave, you have a comment on that?
Yeah, Al, it all depends on what it is you're measuring. If you're going to be measuring, like, say, you're looking at a 30 megahertz signal, okay? So you're going to want to see 30 megahertz, plus you're going to want to see at least 5 or 6 harmonics going out. At 10 megahertz, you go at 60 megahertz, plenty, no problem. Okay, at 30, you're gonna want to go at least 5 or 6. So you're gonna want to go up to 150, 200 megahertz. Otherwise, you're not going to see all of the harmonics. So the reason I'm saying that, if you're ever planning to use your spectrum analyzer for UHF or VHF, it's really important to get the higher frequency model. Because if you're measuring 144 megahertz, 5 times that, 6 times that, you're almost at 1 gig.
Okay, understood.
Right? So, so that's a thing you have to look at. It's not just the frequency you're looking at. You want to look at spectral purity. You want to look at what harmonics that thing is throwing off. And I think most of the energy, it's within the first 5 harmonics or so. You get, even like a square wave's the worst. Within the first 4 or 5 harmonics, that contains 99 or 98% of the energy in that square wave. So that's where that 5 or 6 comes from. It's of that order of magnitude. I don't know if it's 4 or 6 or 7, but it's around that you're going to want to get that up to about that point, because you want to see your spectral purity. And if you're going to be up at, especially going up to 400 megahertz, 5 times that, you're at 2 gigs, right?
Yeah, that's right.
So
good advice.
So those are the things. You can't just look at it's like a scope. You can't look at the single frequency you're looking at, because you're going to want to, because if you're looking at that single frequency, you get a 100 meg scope. You're looking at a 30 megahertz signal, you're going to get a nice sine wave, because it's attenuated a lot of the harmonics. Whereas if you got a 200 or 300 meg scope, you'll start seeing the signal going wonky on your scope, and that's a trigger to say that, hey, I've got some distortion, or I've got something wonky going on. Make sense?
Good advice. Thank you. Like I say, I really wasn't sure, and I saw a big price difference, but I don't want to cheap out on the last $300 or $400 and get something that I regret.
I suspect that you will regret. You'll say $300 and you'll be happy, and then Dave will say something, and you can't measure it, and then you'll be upset.
Yeah.
Yeah. Don't on test equipment. Don't cheap out. Spend the money. Get something quality. Get it well above what you're going to need, because you never know what you're going to need, right? Like, I've got my signal generator I bought. It's a Signalant, and it goes up to, I think, 100 and something megahertz. And when I was measuring the bandwidth of an amplifier I built, I would bottom it out. I was going up over 100 megahertz, and that's it. I couldn't generate anything more. Whereas if I had a 30 megahertz signal generator, there's no way I could measure the bandwidth, right? So don't go cheap. Get something well beyond what you need. It's like, 100, 200 bucks more, spend it,
That's good advice. It's because, well, heck, even the cheaper one's still a fair investment. So spend $1,500 and regret it, or spend $2,000 and get what you want. So that's good advice. Thanks, fellas.
Okay. Well, thanks for that.
And also the other thing, if you get a spectrum analyzer, get lots of attenuators. Get like 3, 5, 10, 20, and get even like a 40 dB attenuator, because the 40 dB attenuator is good for an amplifier if you're going to be looking at the output from a power amplifier, because typically our amplifiers are around 30-ish, 40-ish dBm, right? So if you got a 40 dB attenuator, and you bring it down to like 0 dBm, then all of a sudden you could use your internal attenuator in your spectrum analyzer. So spectrum analyzer, attenuators, hand in hand.
A bunch of these size ones, the little ones, are great. You know, the 30s, the 15s, the 40s, as Dave says. And then I have a 5-watt 31 as well.
Are attenuators 50 ohms or any impedance?
You know what? That's a conversation I want to have, but not tonight, because I want to make sure I make some measurements, because I noticed something a little bit funny a couple weeks ago when I was measuring the impedance of my attenuators, but I think we'll cover that off another day. Holy cow. You've been shopping, Dave. You're muted. You're muted.
What's he holding? A flux capacitor?
No, I was saying Dayton. This is
Dayton.
where I got these from. Dayton, the boneyard.
Yeah, that's good. Okay, thanks, Al. That's great, and look forward to seeing your new toy.
Thanks.
Let's see. Drew, you're up next.
Okay, well, what's on the bench? Last time we were in this, you were mentioning that people weren't building their kits, and I'm one of them. So last weekend I built a QDX, and it works.
Bonus.
And does it ever draw a 9-volt battery down fast? I really wasn't sure it was working to start with, but I did get a decent 9-volt. And those dollar store 9 volts, they don't last worth anything. So it was kind of interesting. Anyways, not a bad build. Lots of little toroids, lots of little tiny wires. Kind of thrilling that way. You certainly find out how many fingerprints you can lose by just cutting them off with a wire. But yeah, it was a lot of fun.
Well, that's good. You're going to bring
Next
it up.
one is the ATU 100, which will be a while.
Okay. Well, you have to bring that out to breakfast on Saturday.
Yeah. It's. I'll tell you, it's really tiny. I don't know if I can show a picture. I'll try.
Well, that's what I say. Like with the show and tell, sometimes really, unless you have an expensive camera, it's almost worth taking a picture of it and then do a share screen to show whatever it is you want to show.
I'm just trying it here, but I don't think it'll work. No, I don't think this is going to work. I think I'll just stop that. Anyways, I did have a picture to show of the little teeny tiny board, because it's smaller than a Raspberry Pi. So it's together with a Raspberry Pi, which is what I'm going to do with it. It's a really interesting portable system, but you have to put 2 power supplies together to keep them going, because the Pi draws about 3 amps, and this thing is good for an amp on transmit.
Okay. Well, you got a second screen up here, but it's not really showing anything. It's just showing all of us.
Oh, well, I can fix that.
Yeah.
I think. No, I can't. I'm going to stop that. I hope. If not, I'll just shut it off. Because, yeah, sorry about that.
Yeah, funny enough, when I go to click on it, I was going to end it for you, but anyway, you did it, so that's good. Now, of course, my screen's all adjusted, so let's see who's.
Yeah, sorry about that.
No worries. All right, thanks for that, Drew. Let's see. Everything's all reshuffled again here. Frank, how's it going? Anything on your bench besides writing up lists? You're muted. You're still muted, Frank. There you go.
Okie doke, we're doing better now. Yeah, I can't see the surface of my bench, so it's full of equipment that I've sorted out for sale, and most of it I've checked out. And then I can't do anything else on that bench until one of you guys decide to buy something. How about that?
I looked at that list and I've built about 90% of it. All right.
Anyway, that's taken up all my time, and now that I've done that, I probably get a chance to do other things. And it was suggested that I start my income tax, so I think that'll take up a couple of weeks.
Okay. Well, Drew's got a comment for you.
I was
Yeah.
just wondering, Frank, I didn't see a list go by. Is that on the SOAREX email list?
Yes, it is.
Yeah, it's a posting.
Yeah.
Okay, so I must have missed it then.
Yeah.
Oh, very good. Thank you.
Okie doke. So that's about it, Peter.
Okay. Thank you, Frank. And Sam, good evening. Anything on your bench these days with electrons running through?
I actually visited a biohacking lab somewhere,
A what?
and a biohacking lab. So
You're missing it.
these are guys who implant NFC chips into their or their hands and stuff. So I got a lot of questions about passively powering RF through the skin, and so I thought I'd ask you guys. Do you guys have any thoughts on that? How to like NFC kind of passive powering sensors that are inside the body?
Well, at my age, I probably don't have to worry about any ill effects, but if I was 20 years old, I might think twice.
Uh-huh.
Dave, you got a comment on that one?
Yeah, Hassan, I can't remember where I saw it, but there was a video I saw where these guys were able to use RF. You're talking about using RF to generate electrical power, right?
That's right. Wireless energy harvesting.
There's some guys, I saw it somewhere where these guys they built this antenna array and they were able to transmit energy across a distance, and they were able to put it across two mountaintops. Mind you, it was microwatts. It wasn't able to power a light or anything, but they had good success on short distances. I can't remember. It was a university, and they were doing.
Marian Seljakic, MIT, Wireless Power Transfer Lab. Is that the guy?
It's who?
Marin Seljakic.
Yeah, I can't remember. I just remember seeing, and they built this huge giant array of antennas, and they were beaming the energy. The trick is to get the energy focused, right, like a laser.
Oh, I know that guy. Wasn't his name like Nikola Tesla or something?
Charlie, you got a comment?
Yeah, I was just going to say I was playing with a group of folks who were looking at wirelessly powering pacemakers and things a few years back, and mechanical hearts. And they were basically just using the same technology that folks are using for charging your cell phone wirelessly. It's basically a transformer that with a gap in between the windings.
Oh, yes, that's right. Okay, so they weren't using like the key standard itself. It was just rolled your own kind of thing.
I believe it was well I don't remember, it was a few years back, but the engineers working on it were really looking at wireless power transfer, and they weren't using any specific standard, but they were using the same methodology as the cell phone chargers.
Cool. Okay. Do you happen to know if there's any, like, how would you store energy? Is there like a supercapacitor small enough to be implanted in the body?
It was being stored with a supercapacitor, but I don't know the details of the parts they were using.
Okay. Awesome. Thank you. It's good to know.
Oh, thanks, Hassan. That's great. Howard, how's things over there?
Pretty good. So I just working away at T41, and I finished the filter board and did some testing on it, and I installed it, and it actually worked. So the receive portion of the radio was working. It's not calibrated or anything. I have a quick video here.
Oh, great.
if I can share it. So just a sec. Hopefully they're there. Can you see that?
Not yet.
Yeah. Not sure why it's. I'm not sure why it's doing that.
Okay, something's coming.
There, can you see that?
I can see all of it.
Can you see that?
It's showing your Gucci section.
I'm not sure what's going on. Anyway, it's working. If you want to move on, I'll see if I can get it, but I'm not sure why I'm not able to share that.
With sharing a video, if it's opened up in a separate window, then you should be able to share that window.
Yeah, I did that. Not sure why. Hang on. Oh, there it goes.
That's it. That's a nice screen.
So yeah, the audio sounds. I had to use an aviation. So.
Yeah, the audio was a bit quiet for us here, but you can certainly see it.
So yeah, so I'm pretty happy about that, and the audio quality is quite good. It's not grounded or anything. There's some hum when you turn the volume down, but I'm getting there. So the next part is the PA section. So
Okay.
that's what I've been doing.
Oh, you mean to let the smoke out section?
Yeah, I know. Now it's going to be the fun part.
Yeah. Okay. Well, thanks, Howard. That's great stuff. Look forward to the next section. Okay. Let's see. Yeah, everything's all mixed up on my screen now for sure. Let's go. Hey, Joe. Good evening. How's it with you?
Things are going well, guys. So last I spoke, I was working on the ultimate kit from QRP Labs, and for the Eclipse, I had the whole thing built, and then in a moment of carelessness, I was using a power supply normally meant for a radio, and you've probably seen those, the Alinco type of power supplies, and they have the detent at 13.5. Well, I brushed that by accident, flipped the voltage to 13.5, and it just blew the board. So I ended up reordering some of the boards, rebuilt all of the active electronics, and then got it up and running again. And then when I finally started testing outside, I wasn't getting anything out. So a little bit of testing on the bench, and I realized that one of the filters, it was the 10 meter band filter, which all the other bands go through. It wasn't allowing signal to go through. So I had to resolder that up, and I was able to get signal through. And then I checked all the other filters the same way, and I was able to get signal through. So after that, I actually did some more testing at home. Simple setup at the house, transmitter, another radio receiving, and I was finally able to pick up the transmission via the computer. So now I'm at the stage of really ready to test outside. So that'll probably happen at some point this weekend.
Boy, you've been busy.
Other than, yeah, it was a bit of work, but glad it was actually a really good exercise. It got me back into using my scope again, injecting signal, checking to make sure signal was going through in a whole bit. The other thing I also did was, I think I mentioned I had ordered the clock kits, the ham clock kit from Thing. I had that built, and that's up and running and working, so which is really good. And then finally, I think I mentioned I was looking to get into what was it, LoRa. So I've been playing around with the Raspberry Pi Picos. So I also finally got today. Some of you may have heard of a company called WaveShare. So they make boards for various controllers. So this is the LoRa board from WaveShare. So that's it there. I purchased 2 of them, and I intend once the eclipse has gone by and I did my work with Whisper, I'll be programming these 2 boards up and then doing tests at distance to see how far I can go on WaveShare. Somebody had a question.
Yeah, Drew does.
Yeah, Joe, it's interesting. I just watched a thing on Meshtastic. Is this related? Is this a Meshtastic system you're running on your LoRa?
I'm planning to do Meshtastic, yeah.
Okay.
So there's some code by WaveShare. First of all, to get the boards running, and then there was actually some software that you can get from Meshtastic actually, sorry, let me step back. The Meshtastic I can image on the Pico, and these boards are one of the boards that the Meshtastic can recognize.
Okay.
So that's what I'm planning on doing.
Peter, that's similar to the mesh network that Dave DAC was talking about at breakfast there.
Oh, okay.
It's an interesting technology. What frequency are you going to pick, Joe?
I've been told for North America, I believe it's 915.
915, okay. Because there was another one at 433.
Right. I'm not sure if we're allowed to do that, although, I mean, technically we're second. Yeah, because we're secondary on it anyway, right? From an amateur radio.
Well, that's where the satellites are. So I mean, and plus you're under 100 milliwatts, so anything you want. But I just wondered what frequency you'd chosen, because the 70 centimeter was kind of interesting, but all kinds of stuff is on there already.
Right. So the recommendations I kept hearing was for 915 for North America. So so I've decided to do that. And part of the other motivation is not only just to play with radio, but I may have made mention that with the Raspberry Pi Picos, I've actually been using them for IoT.
Mm-hmm.
So like Internet of Things. And because at work, part of my mandate at work is I do a little bit of property management. So I've already got 2 Raspberry Pi Picos running as water leak sensors.
Right.
And they're currently communicating via Wi-Fi to a what is called an MQTT server.
Mm-hmm.
That server, it's kind of like Twitter for devices, right? So whenever you want to send telemetry over the internet, you send it to an MQTT server, and then other devices can see that telemetry and then act on it. So for my second trick, because I've got these sensors already working, I want to get Meshtastic up and going, and I want to use Meshtastic. I want to see if the building in Etobicoke, if I put an antenna up in the building in Etobicoke, if I could reach Brampton direct without using the internet. So
without an amplifier?
That's no, without an amplifier. So I want to see, because some people were getting distances of 20 or 30 kilometers when they were, if relatively like on top of a building kind of thing. So I'm just going to do some initial testing. If I need an amp, I'll put an amp.
Yeah.
But I'm going to, just for shits and giggles, try to do it without it.
That's a neat idea.
Cool. Well, you're busy, Joe. I'm exhausted just hearing what you went through. Anyway, good stuff, Joe. Thank you.
Thank you.
Kevin, what's happening on your bench?
Well, not so much on the bench, but the weather was nice, so I actually went out and fixed my antenna this weekend. So there's that. So I did get something ham radio done, and I didn't wait, and it wasn't in -20 weather either. So I'm good.
So you're cheating. Okay, well now you got your antenna done, you can get back to the bench.
Well, I want to set up my Whisper beacon or whatever I'm going to do for the eclipse, so that's why it's like there's a deadline. So anyway. But that's about it.
Okay, thanks. Thanks for that, Kevin. Cherry, what's on your bench these days?
I had.
Oh, sorry, Charlie.
Sorry, did you say Cherry or Charlie?
I said Cherry, but since you got
Okay,
the mic, you might
I'll be quiet.
Yeah, Charlie, you can go first. Yeah, you can go first.
Well, I've had family visiting for a bit, so that kind of took a big bite out of my time. And I've had a few projects that were theoretically running that broke over the past couple of weeks, so I spent some time fixing those. But in order to get into something new and interesting, I've started trying to put together a development environment for Raspberry Pi Pico. And I'm trying to do it with a Linux box, since I'm convinced myself that I'm going to kick Windows to the curb over the course of the next 18 months or so. By the time Windows 11 is mandatory, at that point, I will hopefully not have Windows on any machine. So that has its own challenges when it comes to putting up development environments. I'm not a fan of the Pico Thani IDE, so I've been looking at ways of actually loading files onto the Pico to get them to run to do the things that I want to do. So I have a few little projects that I plan to do with the Pico, but initially I just want to get the environment set up where I can actually start writing code and doing things with it. That's consumed a lot of time.
I bet. Okay, well, thanks for that, Charlie. Interesting. Okay, well, last but not least, of course, we got Cherry.
Yeah, thanks. Yeah, so what I'm doing these days, trying and researching which hamsters is next, so where I can head. So that's what I'm doing. Plus something ham radio. Yeah, I think. One thing I should mention is I'm trying to take down my antenna and replace it with the NFED. The horizontal dipole, I have it for 20 meters. Have been not that great. Have to tune it. Probably I will replace it with the NFED. So I'm trying to do some work on that. So that's the only thing what I'm doing ham radio right now, other than looking at the list of ham radio events coming up soon, heading to Dayton for sure. So yeah, that's all from my side. Thank you.
Okay, thanks for that, Cherry. Okay, well, the timing's just about bang on to our 9 o'clock that we usually aim for. So does anybody else have any other last minute comments, questions? Okay, well, hearing none, I thank everybody for joining us tonight. Good to see you all again, and we'll catch up with everybody, I guess, in another couple of weeks. And with that, we'll say 7-3.
That's great. Thanks very much.
Night, everyone.
Night all.
Night all.
Thank you,
Thanks,
everybody.
bye.
Thank you.
Bye.
Bye.
73 all.
73.